Hi everyone, welcome to day 3 for week 3. We're going to use some of the things that we've learned to develop a new tool. In particular, we're going to develop a new way of looking at functions in the sense of their diagrams. So let's start with the thing that we are familiar with, which is the coordinate system, which is rectangular. What that means is it's our regular grid system where any point xy can be identified by saying that you move x distance along the x-axis and then you move perpendicular a distance of y. So this is sort of like what you would use in navigation, like 2 blocks across and 3 blocks to the left. And it works out fine because, for example, even giving directions from a point A to point B, you can always go left and up, or you can go up and then left. And you're always moving at 90 degrees, which is a very helpful system because we can then use trigonometry and assign find distances using Pythagoras theorem. And it works out. But there are certain scenarios where an alternate system could potentially be of more help. And answering that question would mean answering another question, which is if there is a combination of two variables that identifies a point uniquely. So in this case, the two variables were x and y, meaning horizontal and vertical distance. Now we're going to see that there's another way. Given this xy, I can use the angle it makes with the x-axis, and then I can use this distance from the origin. And this is going to be unique. As you can see, for the same angle theta, I can have two different r values and there would be 2 points which are distinct. And for the same r, I can have two different theta and I would land on a completely new point. So this is what we're going to talk about today in the videos for day 3. This coordinate system has its own name, which is called the polar coordinate system. And instead of writing x comma y, we denote it with r comma theta, where r is the distance from origin, which is the point 0, 0, and theta is the angle made by the line with the positive x-axis. Okay, so we can still think of these as x and y axis. Later on we will see that how the actual polar coordinate system are plotted, but for now we can say that the angle is with the positive x-axis. Now, as we did with degrees, radians, or for any units or methods, we usually, if you define a secondary method, you want to be able to go from one particular representation to the other. So that's going to be our next goal, is to find a relationship between the rectangular and polar coordinates. Now I put some hints here, so maybe before the video you try to get this. So we have two ways of identifying this same point P, xy, which we are familiar with, and r theta, which we are trying to develop. So the hint says use Pythagoras to relate xy and r. Now if this distance is x and this distance is r, then by Pythagoras we already have a relation. So right angle, so x squared plus y squared is r squared, or r is exactly the square root of x squared plus y squared. The second one says use trigonometry to relate x and y. Using trig ratio, I notice that with respect to theta, this is opposite and this is adjacent. So I can say tan theta is y over x, or theta is tan inverse of y over x. So this gives me a way to go from rectangular to polar coordinates. So this is if I want to go from xy to r theta. Now let's see the reverse. Reverse meaning given polar coordinate, we have to find the rectangular coordinates. Now that's easy too. So we use trig ratios for that. And we notice that, for example, sine theta is y over r, or y is r times sine theta. Similarly, cosine theta is x over r, or x is r cosine theta. So this here gives me a way to go from polar coordinate to rectangular coordinate, and this here gives me a way to go from rectangular coordinates to polar coordinate. So this is purely using trigonometry and one extra result, which is the Pythagoras theorem. So let's apply them. Find the rectangular coordinates for these polar points. So x is r cosine theta and y is r sine theta. R is 4 and theta is 2 pi over 3. So it's 4 cosine 2 pi over 3 and 4 sine 2 pi over 3. Let's plug that into the calculator, making sure that it's in radians. So I have 4 cosine 2 pi divided by 3 is negative 2, and 4 sine 2 pi divided by 3 is 3.464. So that's going to be my rectangular coordinate. And you can sort of see that they have to be the same. R4, 2 pi over 3 is roughly, or not roughly, it's exactly 120 degrees. So you would be in quadrant 2 at a distance of 4, and which matches up with x coordinate being negative 2 and y coordinate being somewhere higher. Right, so the coordinates match up. Find the polar coordinates for when this is x and y. So r is going to be square root of 2 squared plus negative 2 squared, which is square root of 8 or 2 square root 2. And theta is going to be tan inverse of y over tan inverse of negative 1. Now here you have to be careful about which tan inverse value to use, right? What quadrant is this point in? 2 negative 2 means it's in 4th quadrant, and ASTC tells me that tangent is negative in 4th quadrant. So let's find tan inverse of negative 1. Tan inverse is 1 at 45 degree multiples, right? So negative 1 would be right here, negative 45, which would give me this as 2 pi minus pi over 4, which is 7 pi over 4. So this would be 2 root 2, 7 pi over 4. Now, since we have a relationship between x, y, r and x, y, theta, not only can or should we be able to change points into one system and the other, we should also be able to express equations in different systems. For example, let's say this is an equation in the rectangular coordinate system. Given x squared equals 4y, you want to write this in polar coordinates. So all you have to do in this case is remember that x is r cosine theta and y is r sine theta, and you plug these in there. So you get r squared cosine squared theta is 4r sine theta. Now you can factor out one of the r's, cancel it. So the equation is r cosine squared theta equals 4 sine theta. What this means is, if you were to plot this in the rectangular coordinate system, that's a parabola. And if you plot this in the polar system, it should give you the same result, and it will. Let's look at a last example for this video. Now, given in polar form, how do we convert it to rectangular coordinates? Right, so that was converting from rectangular coordinates to polar coordinates. Now there can be more than one way to do this. Let's see. One of the relations that I know is that tan theta equals y over x. Right? And I also know that r equals square root of x squared plus y squared. Now this gives me that there is a triangle where this is y and this is x and this is r. Now what is secant theta? Secant theta is 1 over cosine theta, which is 1 over x over r, which is r over x. So this just gives me r equals 5 times r over x, or x equals 5. So this is nothing but just a vertical line, x equals 5. So essentially going from polar to rectangular can be a little tricky, but all you have to do is use this relation to express the theta part in terms of y and x, and then cancel out whatever may or may not cancel, and if they don't cancel, then you use the Pythagorean part to convert r in terms of x's and y's. That's the end of this video. Next video, we're going to be introduced to how to start thinking about plotting functions in the polar coordinate system.